is Markus Müller, and he will talk about the role of thermal fluctuations in many-body localization, rare events, effective mobility, edges, and super Arrhenius behavior.
Mr. Pointer. Yeah, I would like to thank the organizer for putting together this nice meeting that is quite on a broad range of subjects. So this is again about many-body localization, but this time there will also be replicas, don't be afraid. And this is a work we did with Valentina Rose from École Normale. So I'm going to review many-body localization very quickly, pedagogically for you in a different way from Antonella, so maybe it's complementary. So I see it as an interesting way to avoid thermalization, to get non-ergodicity in a quantum fashion rather than in a classical glassy fashion. Okay, and that's always interesting if you're non-ergodic because you can store some information in your system, right? That doesn't go away, and of course this runs against the dogma that everything should thermalize and become dull at long times. So if you ask, how can you get non-ergodic? Usually it's by barriers in classical glasses. Then if you turn on quantum mechanics, you can tunnel under the barrier and you think it would get worse with non-ergodicity because you get delocalized wave functions, plane waves that we love. Right? But if you put disorder on your potential, that's just a single particle picture, and you have a hopping from well to well with disordered potentials here, then if disorder is very strong, then the eigenstates of a single particle will be localized in space. That means if you put the particle here in the beginning and you wait a long time, it doesn't diffuse at all. Right? And that's what Anderson got the Nobel Prize for this realization. If you put many particles and they interact, the question is, can this survive, or is this just an artifact of a single particle? And usually we would expect that interactions introduce dephasing and they destroy interference and you go back to equilibrium. But, so the idea is that if there's another particle that interacts with this localized wave function, it can exchange energy. This particle goes up in energy, it gives energy to this localized wave function that can move over here, and then sort of you have destroyed localization of this red wave function, which now goes to the pink. Then there will be another particle that pushes it further and so on. But there's a catch, however, because if you think that these interactions dephase like that, there's a loophole. Because the energy that you can get from another particle, if that other particle is also localized, will be quantized, and so you may have a too big mismatch of energy that you can get from your environment, and if the mismatch is too big, then you will just not be resonant and you will not hybridize with between here and here. Okay, and so many-body localization is the idea that you can have a self-consistent state where your local environment is so discrete and so non-resonant that nothing is moving very far. Everything is just oscillating locally and nothing happens. Okay? So it's a crisis of resonances if you want. Right? And so this is basically an old idea. Already Anderson and Fleischmann asked, do interactions matter or not for localization? And they, I think, mostly got the right answer, that if the interactions are weak, short range, then you kind of localize despite of interactions. Then Basquiat, Lehner, and Altschuler took this idea further and asked, what does temperature or mean energy do to this picture? And they realized, well, very naturally, that when you go to high temperatures, you have a lot of excited states. You have many more scattering channels, so temperature tunes sort of the number of resonances that you have, and then there should be some window at least where temperature could tune a delocalization, okay, because you have more resonances here, so if you were localized here, then you will be delocalized up there. And so they predicted that there will be a transition at finite temperature, even in one dimension, where usually we think there cannot be phase transitions, between a transporting, equilibrating phase and a phase that is completely non-ergodic. So that was very spectacular. A little later, Hughes and Oganessian realized that if you put your system on a lattice, for example, electrons on a lattice at top, then the temperature being much larger than the bandwidth has essentially no further effect than temperature at the bandwidth. And so they said even at infinite temperature, you should be able to have this phase transition. And indeed, numerically, you see that very well, that it is there, right? So that was the first thing. Then came Imbri and proved in a 1D spin chain under this physical assumption that is very reasonable that many-body localization exists over here, right? When the disorder is very large, quantum fluctuations are weak, then you have really these integrals of motion and non-ergodicity. But the proof works only for 1D. It's very simple to see why, but I don't explain it. Maybe if you want to go to higher dimensions, I think it's not the bug of the proof, but it's a feature of the proof that it doesn't work. So we believe there's a fundamental reason why only in 1D the proof works. And second thing is the temperature doesn't appear in the proof. It is actually anywhere in the spectrum. And you can ask, why is that? And if you think more about it, you come to the realization that probably this idea here is just about the strong crossover, but truly speaking, there is no temperature-driven transition because any system down here could locally look like it is hot, and these hot inclusions would move and destroy localization. So probably the correct phase diagram is actually a vertical line down from this point that we know to exist, and here you have just a very badly conducting phase. Okay. The nature of the transition up here is actually driven by, we believe, by rare events. Those events that actually destroy localization altogether in higher dimensions. In one dimension, they can be contained over here, and then they explode at this point. It's a kind of an interesting kind of explosive phase transition. Okay. In higher dimension, you probably only have a crossover. So now it's at the end of the story. No, I would say there's still quite an interest to ask what does temperature do, for example, in this very badly conducting phase. Just to say that there is some kind of creepy transport here is not yet very useful. If this is exponential minus 1,000 in conductance, you don't really care about it, so you kind of want to know what happens here, and that's the topic today. How does temperature or mean energy modulate the localization tendency, or what happens in the quasi-localized regime? Okay. Now let's think about this many-body localization a bit more formally. Basically, we say our system has sort of a classical part and a quantum part. So that's terms in the Hamiltonian that all commute, like an Ising model or density-density interactions or random fields or so. And then there are terms that do not commute with those terms, like hopping terms or scattering terms for fermions or so, and they give the system dynamics in the first place, and you hope that they restore ergodicity if they are strong enough. But the whole business of MBL is to ask if this is sufficiently complex and this is sufficiently weak, is ergodicity dying or not? Okay? And somehow the interactions are sitting in here, but I haven't said where. Okay. So the idea is that HC, this classical part, must have a discrete spectrum locally, and it should be sufficiently inhomogeneous so that this guy has a hard time to implement resonances which will mix and lead to diffusion. Okay. So, where are the interactions here, right? Or what is the role of temperature? So far, we haven't talked about that. So, the interactions may have a very different effect depending on whether they sit mostly here or here. Okay? So the standard setting, what I told you about before, what Basco, Alain, and Altschuler were thinking about, and also Anderson and Fleischmann, is to say that the interactions basically introduce scattering terms. So, for example, if you have electrons in a potential, they hop, and now they also interact, then they enhance the diffusive character of the model. But you can also have interaction-induced localization, basically, if you put the interactions mostly in the classical part, for example, a spin glass or electron glass, like Hamiltonians, where you say, well, I have basically classical spins or charges that sit in some locations, and they interact in this way that, of course, commutes with occupation number operators, right? And the only quantum dynamics comes from the hopping term. And this and that is, these two ways of introducing the interactions into the system are totally different. And actually, if you take that to the extreme, you can even ask, if I have no disorder at all here, and if these interactions are also not disordered, but only my configuration is disordered, is that producing a sufficiently complex classical Hamiltonian such that these terms have no chance to make resonances? And that's an old idea by Kagan and Maximov, a very interesting one that was rediscovered by many groups recently. And it almost works through. It's susceptible to the same kind of problems as these rare events that destroy many-body localization in other situations. But there is an asymptotic kind of localization that survives without disorder. So a bit a quantum analogon of this, of the stories that we heard yesterday. Okay. Now today I want to show you what you get from this effect of type 2, where you put the interactions mostly in the classical part. And I ask in particular if this classical part is fluctuating because you have thermal fluctuations of your occupations. What does a conducting electron do if it sees a fluctuating potential? And then in a second part, I ask what are thermal fluctuation effects on mobility edges that you may have, and what is the result on the transport. But the main part will be this thing here that I start with a strongly interacting classical Hamiltonian. If you may think of a spin glass, if you wish, actually. And I give some hopping here. So this could be electrons that interact with Coulomb interactions, if you wish, and they have hopping. Or you take spins, your favorite Sherrington-Kirkpatrick, or a ferromagnetic random field ferromagnet with a transverse term that doesn't commute with this. And then you ask what is going on in terms of localization. Okay? So let me switch to spin language that's maybe more familiar to you. Okay. So what is the role of this term? Very simple. It creates an effective local field that each spin sees. So it sees not only this term, but also the interaction with its neighbors. And now let's think of some path along my lattice. And each side has its neighbors, and these neighbors create an effective field. But it's not constant, it fluctuates because these neighbors have thermal fluctuations. Okay? So at every instant of time, essentially, I see a local effective field. And I can ask what is the distribution of these local fields in space. And there is an interesting thing to say about that. So if the neighbors here are strongly correlated and interacting with each other, then you can get gaps or pseudo gaps in the distribution of fields, as we have seen also yesterday in Francesco's talk, right? And I'll talk about that later. But if your neighbors are weakly correlated, or they don't even talk to each other, for example, this doesn't talk with that one, or you are at high temperatures, then, and also if the distribution of those guys is symmetric, then this distribution of fields that you see over all space is actually independent of temperature. You have fluctuations, but the fluctuations average out. So if you take a sample over the whole, over your whole material, then you see always the same distribution. And then you can ask, is there any effect at all if temperature doesn't alter this distribution? Yes, there is. There are still thermal fluctuations on site. You don't always see the same field, and that may have an effect. Actually, it might even have a quite strong effect. So let's now think about the following problem, that we have spins. They see an effective field that fluctuates slowly in time, very slowly. And you have transverse terms, so some spin flip terms that go like this. And you ask, if I flip this spin, can this spin flip propagate through the system, or does it get localized on this random local field? Okay? And so the distribution of fields that you see on a given site is this local random field plus exchange with the neighbors, and that fluctuates in time, and so that has a thermal distribution. So you have a few delta peaks on each site. Now, if you ask whether a spin flip can propagate to infinity, that's a complicated problem, but there's an approximation. When this term is weak, relatively weak, then you can do leading order perturbation theory. You just flip one spin after the next. You do high order perturbation theory along a path. For each step, you get the J perp and a denominator. The denominator at zero frequency is just the local energy. Okay? And now you have to sum over all paths from your original site to the boundary.
So this is, you're treating completely adiabatically.
Yes.
The age effect.
Right. Yeah. You may question, is that a good thing or not? But if it's very slow, I think it's fine. So you can do this on any finite dimensional lattice. That's basically what Anderson did in his 58 paper for electrons. You can also put this on the beta lattice, and that's kind of popular because for non-interacting electrons, you can solve that exactly. So maybe we'll do that too. So now you get the matrix element to go from 0 to somewhere in the boundary. You square that, that's Fermi-Golden's rule, for the decay rate to go to the boundary, okay? And what you now want to know is, when the boundary is far away at the distance L, is this decay rate finite, or does it decay to 0 in the thermodynamic limit? If it decays to 0, then you're localized. You cannot decay, you cannot escape to infinity. You stay close to where you are. If gamma becomes 0, then this decay rate is finite, and that's the delocalization transition. Okay? Why could it be? Why is it like that? Well, because essentially you have an exponential number of terms here, and each one is exponentially small, and depending on what the numbers are here, you can have this transition. Right? Okay. Now, there's an interesting mapping of this approximate formulation of the localization problem to directed polymers. Many of you may have seen that. You just take this locator expression and you write this as exponential of its log, and then you see that it's nothing else than a sum over path of a polymer that you can put there, and there's a random energy which has this form. But you should always remember that this comes from formal perturbation theory, and that is not just sacrosanct valid at all J perp, for example. At some point when you approach delocalization, it becomes dangerous to use this form. Okay. Now the idea is that you ask about this lifetime or decay to infinity, not at a single time, but a sort of time averaged. You ask, if I wait long enough and my age effective are fluctuating slowly, maybe at some point I have a better decay rate to infinity, and if I wait the right time, then I have a better decay rate overall, right? So that corresponds to computing an annealed average over these decay rates. And that was actually proposed and analyzed in this paper a few years ago, and what the authors found is that that thermal fluctuations could drive a delocalization transition. So here is disorder or inverse disorder, and they said if you turn on fluctuations and if they are good enough, then rare fluctuations can give you some small denominators here, and so your tendency to get to infinity can be strong enough and you delocalize. I found that mind-boggling a bit, but also very interesting. If fluctuations can induce delocalization, it might mean that there could maybe be a bistability at a given disorder. That means there could be a phase where everything is fluctuating, and therefore it is better delocalized. So there's a delocalized phase that is self-consistently noisy and fluctuating. Or if you prepare the system in a quiescent state, it just remains like that because it's more localized. And that could have suggested that the many-body localization transition is maybe a kind of first-order transition where you go from here to here in a coexistent type of manner. But if you think more about this, somehow you think, no, this cannot be. But there was this prediction, and so I was very puzzled for quite a while. But it turns out that this is not true. Fluctuations cannot induce delocalization. And the reason is relatively simple to see. If you go to the beta lattice, just for the sake of argument, then we know that delocalization happens actually when you come from the strongly localized side, when one best path from the origin to one of these leaves here has a non-decaying matrix element. One can also say in some jargon that the localized phase is a frozen RSB-like phase. And at delocalization, you still are dominated by the best path. Okay. Now, if this non-decay to one of the leaves is not occurring with the typical realization of your effective fields, but if you have to wait for a rare fluctuation, then your lifetime or your decay rate is still exponentially rare, because this rare fluctuation will be exponentially rare in the size, and so that doesn't help you. So if you have to wait for a rare fluctuation, then you don't get order 1 decay rate. Okay, and that means you will only delocalize when the typical age effective, so the typical thermal fluctuation gives you a delocalization. So whether you turn on or off thermal fluctuation, it doesn't help you about delocalization. Also in finite D, you can make this argument, and it's unlikely that you can ever delocalize by thermal fluctuation. So where is the catch? So what went wrong somehow? So we had this expression that the decay rate is actually, or the log of the decay rate should be the quenched average over the local disorder, but then the annealed average over the thermally fluctuating contributions from the neighbors. Okay. Now the problem here is that you have small denominators, and they are dangerous. So if you take an annealed average over this thing, that can blow up in your face. And you have to remember that if you have too small a denominator, there will be self-energy corrections that kill this denominator. And you should also remember that physically such a matrix element here, this whole product is a matrix element to go from 0 to f. That can physically not be bigger than 1, but if you make these denominators very small, it will be exponentially large here. And so to cure this problem, you should at least put here an upper bound on what this expression can be. Okay, that's maybe a bit crude, but it helps understanding what's going on. So you have to limit this, otherwise you are dominated by rare events where this expression is exponentially large, and wrongly so, because that's unphysical, right? Now, the whole problem, if we put this on a beta lattice, for example, that has the problem that you have to decide which is the best path here, and that's a complicated calculation. So to understand the physics, it's simpler to just take a 1D path or one path in this tree, if you like, right? So just one chain, and so we have just one product over all sides in this chain, okay? And on each side, we have this fluctuation of the effective local field. And now we ask, what is this decay rate now? And that's a simple calculation that you can do, and it's actually replica-like, so you could certainly do this with replica too, but it's much easier without, I guess. So you ask, what is the probability of the fluctuating disorder to be such that this thing has a decay that goes like e to minus gamma L. So an average decay rate that is gamma, so you ask that this sum here adds up to minus gamma L. Okay, you compute that, and you get that this sigma here, the large deviation function, is the Legendre transform of this simple expression here. Right? That's a kind of a monocentric, if you want. Now, if you ask what is the lifetime or the decay rate and eventually the conductance averaged over time at zero frequency, then you just take integral over all possible spatial decay rates, and you ask how probable are they, and you take the maximum, right? And that gives you the answer for the annealed time average conductance, okay? And that you compare to the typical conductance, that is when you freeze a certain typical thermal fluctuation of your fields, but then they don't vary, and you ask what is the conductance now. That has, of course, a different expression. And if you look what you get out, here is the frozen conductance. I plot actually minus the log of the decay rate over L, so here the decay rate is very small. And here is the fluctuating one, so you see that the decay rate goes up dramatically, but it never, you never get to zero, so you're never getting really conducting, because at this point, the best thermal fluctuation gets such that the decay rate gamma becomes zero, and at that point you have to remember that gamma cannot become negative, and then you get the phase transition here in the localized phase. And when you ask when do I delocalize, it's exactly at the same point then as whether or not you have thermal fluctuations. So you see that if you don't take this constraint into account, you would fool yourself and think that you delocalized earlier. Right.
So maybe you should.
Yeah, I will probably skip the second part and right. So the important thing is you have sort of a phase transition in rare events within the localized phase, right? So classical interactions will not delocalize you, they just enhance the exponentially weak conductance. Now you can ask, are there other effects that you can have? If you have a classical modification of the density of states, for example, so if you have a spin glass, then you have this P of H, which has a pseudo gap. It fills as you have temperature. And you can ask, does this modify, for example, the presence of a mobility edge? You know, if you have a density of states that is not constant, and you ask where do I propagate well, quantum mechanically there will be a mobility edge. Up here you are delocalized, and down here you're localized. And now you can ask, if I switch on temperature and I modify this density of states, does it move these mobility edges? The answer is yes, a little bit, but very little. Okay? There's a much more interesting effect that is due to scattering, and that I don't have time to explain to you. But the upshot is the following. If you scatter close to the mobility edge from thermal excitation, then there's an energy uncertainty of states that are close to the mobility edge because they scatter from cold excitations down here. And if that scattering rate is sufficiently large, then you cannot distinguish anymore that here there's a discrete spectrum, and so you get an effective mobility edge, and it comes down as scattering goes up, so as temperature goes up. And the upshot is that even in 1 and 2 dimension, you get the notion of effective mobility edge. At 0 temperature, you can have no mobility edge in low dimensions, but due to interactions, you have something like an effective mobility edge that diverges only in the infinite temperature limit. And in 3 dimension, where you do have a mobility edge at finite energy, it comes down and relatively rapidly as a function of temperature like this, with a correction that is much bigger than temperature. And that is probably relevant at quantum phase transitions that are associated with localization. And so now I'll conclude. So the take-home message is that interactions are not just one kind. They can be sort of classical or quantum, and what they do is very different, and it's kind of rich what can happen. So classical fluctuations, the first part, they enhance conductance in the localized phase, but they don't delocalize. So if you want them a temperature-driven transition, that doesn't help you. But if you are asking a more modest question, if you already know that there is, for example, a mobility edge in 3 dimensions, and you ask what does temperature do to that, then the mobility edge comes down because you have significant scattering of hot particles close to the mobility edge, and that smoothes it out, and that has a strong effect on activated transport. Okay, with that, I'll thank you for...
Are there any questions? So, we should, now we have a coffee break. Now we stop, and we start in approximately